Ever since we could count, we've been playing with algorithms for manipulating numbers. When Euclid discovered his famous algorithm for computing the greatest common divisor of two numbers, he wrote about it in his book, The Elements of Geometry, 300 years before the Bible was written. Now, it's been 2,000 years, and still there are some questions that we do not have algorithms for. And maybe the most important one of them is factoring. We do have a quantum algorithm for factoring. So if we had a quantum computer to run it on, then we would be able to factor numbers efficiently. And we also have an efficient algorithm that can test whether a number is prime or not, an algorithm for primality testing, which is an easier problem than factoring. In this video, I want to discuss how these algorithms work and why they work. So let me now introduce the problem of factoring. So you're given a number n, and the goal is to find the prime factorization of n. Factor n into its prime factors. Now we're interested in finding algorithms that are efficient in terms of the number of digits of n. So there is the naive algorithm which try to divide n by 1, then 2, then 3, then 4. This algorithm is not efficient, okay, because it takes an exponential number of steps in terms of the number of digits of n. A second problem is to just check whether n is prime or not. And this is an easier problem than factoring. So at a very high level, the approach we're going to pursue is we're going to try and find a nice witness to the fact that n is not prime. Now, any algorithm for factoring n must inherently, ultimately compute a witness that shows that n is not prime when n is not prime. So an obvious witness here is the factors of n, okay? But that's not a nice witness because it's not easy to find the factors, at least not directly. What we really want is a witness that is easy to find, easy to verify. It's easy to verify that it is a witness. And maybe a third feature that we'd like is we'd like the witness to lead to factors of n. Okay. And what I'm going to discuss here is several candidates for these witnesses. And I think it's really interesting how they work. Before I get there, I need to introduce some basic concepts from group theory and number theory. So I'll do that first, and I'll be fairly quick here. So first, what is a group? A group is a set with a multiplication rule. There should be the number 1 in the group is the number that when you multiply with 1, you just get the original element. And every element A in the group has an inverse. So you can also divide by numbers in the group. So that's a group. And when you're given a group, the group may have subgroups, namely a subset that is also a group. And if the group has a subgroup, then you can talk about the cosets of that subgroup. These are the sets XS, where X is an element of E, which is made up of all the products of the type X times S, where S comes from S. And a basic fact is that the cosets of S are either equal or disjoint. And that's because if two cosets intersect, then you can actually show that one is contained in the other. Okay. And this means that when you have a subgroup S of E, the cosets of S partition all of E. And in particular, that means that the size of the subgroup S must divide the size of E. Okay, so a consequence of this is that either the sizes of the two groups are equal, or the size of S is at most 50% of E. And this is really the key fact that we'll need. It's used to prove bounds on the error of the algorithms that we'll find. All right, now let's review some basic facts about numbers. The first fact that I want to review is that if n is a prime number, then there are no surprising square roots of 1. Meaning that if x squared is equal to 1 modulo n, this can happen only if x is plus or minus 1 modulo n. Okay, and that's a fact that's true for n that's prime, but not true for n that's not prime. And why is it true? Well, if x squared is equal to 1 modulo n, that means n divides x squared minus 1. But x squared minus 1 is equal to x plus 1 times x minus 1. So that means n must divide one of these two, because n is prime. And if it divides one of those two, that means that x must be equal to plus 1 or minus 1 modulo n. All right, so that's a basic fact that will be useful to find witnesses to the fact that n is not prime, right? The numbers that are not prime are the ones that have interesting square roots of 1. That's what it says. Okay, so another useful fact that comes from Euclid's greatest common divisor algorithm is that the greatest common divisor of a and n can be expressed as a linear combination of a and n with integer coefficients. And this means that the set of numbers that are relatively prime to n, this set, is a group. Okay, because this set of numbers has a feature that, here you have 1, so that means for every such number a, it has a multiplicative inverse modulo n. A times b must be equal to 1 modulo n by this equation. So the set of numbers that are relatively prime to n form a group under multiplication modulo n. So let's write phi of n to denote the size of that group, and let's write the order of a to denote the minimal power r with a to the r equals 1 modulo n. Such an r must always exist, because if you start powering a, at some point you will repeat a number, so you will get a to the p is equal to a to the q, but then a to the p minus q must be equal to 1 modulo n. Euler's theorem says that if a is an e, then the order of a must divide phi of n. Okay, which means that a to the power phi of n is equal to 1 modulo n. That's because if you look at 1, a squared, and so on, this set forms a subgroup of e, and the size of the subgroup is equal to the order of a. So because of what we talked about before, the size of this subgroup must divide the size of e, which proves the theorem. Finally, we have the famous Chinese remainder theorem, which says that if you have two relatively prime numbers, m and n, then for every a, b, there will be a number c that's equal to a modulo m and b modulo n. Okay. So every choice of a and b is realizable by some c. All right, so those are some of the basic tools I'll be using. Another nice fact is that you can actually write down a formula for phi of n if you know its prime factorization, and this is the formula. Okay. That's not too hard to verify. All right, so those are some basics, and now we have those under our belt, we can start to look for some interesting witnesses. So the starting point is this fact that we just discussed, that if n is prime, then there are no surprising square roots of 1. So a natural candidate for a witness is an x that is a surprising square root of 1. Okay. And such a witness is very useful because you can also use it to factor n. If you find such an x, then because n must divide x squared minus 1, right? But n does not divide either of these two factors, and x without loss of generality can be chosen to be less than n. The GCD of n with x minus 1 will be a non-trivial factor of n. Okay. So every witness of this type leads to an interesting factor of n. if you find an interesting square root of 1 modulo n, you also obtain an interesting factor of n. But the problem with this witness is that there are not many of them, so they're going to be hard to find. You know, in particular, if n is just the product of two primes, then it's easy to see that there's only 4 such interesting potential such witnesses, because if x squared is equal to 1 modulo n, then modulo p x can have only the boring square roots, plus 1 or minus 1, and modulo q, that's also true. And by the Chinese remainder theorem, this leads to only 4 possible values for x. 2 of them are plus 1 and minus 1, so there are actually only 2 interesting values which are not plus 1 and minus 1. So there are not many witnesses of this type. However, you know, maybe there's a different approach we can take, which is to try and take square roots in some way. And this is the first idea that's very useful to understand where to go from here. So let's set let's say we know phi of n. Okay, so phi of n, so we have phi of n. Let's write it as 2 to the e times k, where 2 to the power e times k, where k is odd. In other words, we take out all the factors of 2 from phi of n. The intuition behind this witness is we're going to start with a number, you know, in the case of prime n, this number will be 1, and then we're going to start taking square roots. And if n was prime, then the first non-1 square root that you see will be minus 1. So in the witness, we'll insist that all of these numbers are not minus 1 modulo n, and this last number here is not 1 modulo n. That's the witness. All right, so now let's analyze this witness. The first claim I want to make is that if n is prime, then there is no witness. And that's because if n is prime, then this number will always be 1 modulo n. And that means all of these square roots here will either be 1 or minus 1. And so at some point, either you'll have a minus 1 in this part. If you don't have minus 1s anywhere there, the entire sequence has to be 1. So there is no witness when n is prime. If n is not prime, I claim that a witness leads to a factor of n. And that's because if this number is not 1 modulo n, then x must have a common factor with n. And so the GCD of x and n is a factor. If on the other hand you have a witness where this is 1, then you see if you go down here, none of these are minus 1, and the end here is not 1 either. So somewhere along the way you have to discover an interesting square root of 1, which, as we discussed earlier, leads to a factor of n. So for witnesses that are for numbers n that are not prime, a witness leads to a factor. One of the problems with this definition is that there's no clear way to check that a number x is a witness, because we don't know how to efficiently compute phi of n. But here's a different definition, which is easy to check, at least on a quantum computer. So we'll say x is a witness of type 2 if either x is not in E, okay, or if x is in E, we'll say it's a witness of type 2 if the order of x is even and x to the power order of x over 2 is not equal to minus 1. In other words, this number is an interesting square root of x, interesting square root of 1. Now it turns out that you can compute the order of x efficiently on a quantum computer. And so this criterion, whether or not x is a witness of type 2, can be efficiently checked on a quantum computer. Moreover, every witness of the first type here is a witness of the second type. That's a claim. And here's why it's true. Well, if you have a witness of the first type, and then one possibility is that it's not in E, okay, and it's a witness of the second type. But if it is in E, then the order of x is well defined. So let's write the order of x like this. Let's take out again all the factors of 2. And let's consider this sequence here. So this is x to the k prime, x to the k prime squared, and all the squares all the way up. Because the order of x divides phi of n, this k prime here must divide k. And that means the sequence above consists of numbers that are odd powers of the sequence below. All of these numbers are odd powers of the sequence below. So you cannot have the order of x be odd, because that would mean that this number is 1. That would imply that this number is 1, but that would make x not a witness. You cannot have one of these numbers to be -1. Okay, you cannot have this, because that would mean there would be a -1 down here, which would lead to a -1 down here, because -1 to an odd power gives you again -1. All right, so every witness of this type is a witness of the second type. And the second criterion is easy to check on a quantum computer. Now, so that gives you at least, it will suggest in a second, a quantum algorithm for factoring, which we will discuss. But there's one more witness I want to talk about, which is inspired again by this witness. In this witness, you see you have your phi of n, but when n is prime, phi of n is equal to n minus 1. So that suggests a different kind of witness where you replace the phi of n with n minus 1. Otherwise, I have the same description. And this is the Miller-Rabin witness. Okay. And the intuition is, when n is prime, the two definitions are the same. So there will be no Miller-Rabin witness for the same reason that there's no Shor witness when n is prime. But the concept of a Miller-Rabin witness is quite different. In particular, although a Shor witness leads to a factor of n, we don't know how to use a Miller-Rabin witness to find a factor of n. On the other hand, we can actually check a Miller-Rabin witness efficiently because we can compute n minus 1. So we can actually check just with a classical computer that x is a Miller-Rabin witness. So that's the power of the Miller-Rabin witness. Ultimately, what I'm going to prove is that if n is not a prime power, then both types of witnesses, the non-witnesses for both definitions here, are contained in proper subgroups of E, in strict subgroups of E. Which means in particular that the number of non-witnesses is small. It's at most 50% of the size of E. Okay, so that means that there are lots of witnesses. At least half the elements from 1 to n minus 1 must be a witness for both types of witnesses. That's in the case that n is not a prime power. When n is a prime power, I can prove the same fact, but only for the Miller-Rabin witnesses. Okay. And these two theorems now give algorithms for factoring and primality testing. The Miller-Rabin algorithm is very simple. It looks like this. Sample A uniformly at random and check if A is a Miller-Rabin witness. By these two theorems, in the case that n is prime, there will be no witness. In the case that n is not prime, then 50% of the choices of A will lead to a witness. Okay, so that's an algorithm for checking if n is prime or not. And here's Shor's algorithm for factoring. Well, for Shor's algorithm, it's a little more complicated because we have a statement about the witnesses only in the case that n is not a prime power. So we need to eliminate that case first, which is easy to do. We'll first check that whether or not n is a perfect power. And we can do this by, if n is equal to the power of some number, an integer power, then this power r is at most log n. So we can check for all L up to log n whether or not n to the power 1 over L is an integer. And this can be done just with binary search. Okay, so it can be done efficiently. And there's only log n powers that we need to try. That's not too many. So if in fact n is equal to m to the r, we found a factor in this way. Otherwise, we're in the setting of this theorem, so we can sample a random element and check whether that element is a Shor witness of type 2, which can be done efficiently on a quantum computer. And if it is a witness, we obtain a factor. Okay, because we actually find a number that's a non-trivial square root of 1. And if it's not a witness, we repeat this process. Okay. So that's Shor's algorithm for factoring. It can be implemented efficiently in a quantum computer. All right, now the only thing I need to do is prove these two theorems to you, which are very nice proofs. So let's start with the first one. So let's say you have a witness. It's either a Shor witness or the Miller-Rabin witness. So either you have this or this. And let's say n is not a prime power. So here's the idea. Let's pick L, an integer, a non-negative integer, in such a way that L is maximized and there's some b with b to the power 2 to the L equals minus 1 modulo n. So choose L in this way. There is always a choice for L that works, because if you set b to be minus 1, then L equals 0 works. Okay. So choose L in this way. And now I claim that this set S is a subgroup of E containing all the non-witnesses. It's a subgroup because you can see that it's closed under multiplication, and it's a subset of E, right? If you take, if x to the power 2 to the L times k is plus or minus 1, then the square of this number is equal to 1 modulo n, which implies that x is in E, right? X to some power is relatively prime to n. So S is contained in E, and moreover, it's closed under multiplication, so it's a subgroup. Finally, it contains all the non-witnesses, because every non-witness here, if the non-witness has 1 in this location, then it will certainly be 1 here. If the non-witness has a minus 1 somewhere here, then that minus 1 must occur, before L or at L. So again, you'll have the condition that this power will be plus 1 or minus 1. So all the non-witnesses are contained in S. And finally, I claim that S does not contain all elements of E. And here I'll use the fact that n is not a prime power. So let's write n as a prime power times something that's relatively prime to that prime power. Then by the Chinese remainder theorem, there must be a number C that's equal to b modulo p to the r and equal to 1 modulo m. If it's equal to b modulo, because it's equal to b modulo p to the r, when you raise it to the power 2 to the L times k, that's equal to minus 1 to the power k by the choice of b, which is equal to minus 1 mod p to the r. On the other hand, if it's equal to 1 modulo m, then this power is equal to 1 modulo m. But that means that C cannot belong to S. Okay. But C does belong to E. Okay, C does belong to E because if you raise it to a large enough power, you get 1 modulo n. All right. So we found the subgroup that contains all the non-witnesses but is not equal to E. And for the last part, if n is a prime power, I claim that the non-witnesses for the Miller-Rabin witnesses are contained in a proper subgroup, and that's because when n is a prime power, then phi of n is equal to this, p to some power times p minus 1. But if you have a non-witness A then either there's a 1 here or there's a -1 somewhere here. In both cases, this number here will be 1 modulo n. But if it's 1 modulo n, that means a must be in E, and a then -1 is 1 modulo n. And that means the order of a divides both n-1 and phi of n. In particular, it divides the greatest common divisor of those two, which in this case is equal to p-1. So that means that this set AS is a subgroup containing all non-witnesses. Okay. So all we need to do now is to prove that this subgroup is not all elements E. And that you can do just by coming up with an explicit example. Consider this number 1 plus p to the power r minus 1. If you'd raise it to the power p, by the binomial theorem, what you get looks like this. And this expression I claim is 1 modulo p to the r. And that's because every one of these terms is 0 modulo p to the r. Okay. All of the terms in the middle, except for the terms at the end, the binomial coefficients are are divisible by p, and the numbers here have powers are at least p to the r minus 1. The very last term here, this number is 1, but this number is larger than p to the r minus 1 again. So this entire expression is equal to 1 modulo p to the r, and that means the order of this number must divide p, which means it must be equal to p. So the order of this number is equal to p, but p does not divide p minus 1. P does not divide p minus 1, so this number cannot be inside S. Cannot be inside S. And that means that S is not equal to E. All right, so I hope you enjoyed this video. And I think it's very interesting to understand what other kinds of witnesses can help with factoring.